Welcome to this interesting topic, light. So this is the continuation of waves. We looked at a general wave where we looked at properties such as amplitude, wavelength, and how to calculate parameters such as speed. Then we also looked at sound waves. In this video, we're going to start a new type of wave called light. So light is just an example of a wave. With that being said, this video is going to be delivered this lesson is going to be delivered into 3 videos. So in the first video, which is this one, we're going to take a look at what is called electromagnetic spectrum. Then in the same video, we're also going to take a look at a property of light called reflection. In the next video, we'll look at another property of light called refraction. Then we'll end up this topic with a third video, which is going to be focused on lenses. With that being said, let's get started. So we're going to start with this diagram here. So this diagram is a very special diagram that teaches us about what is called electromagnetic waves. So just like we have sound waves, there is a type of another type of waves, or an example of a wave, which are called electromagnetic waves. So we're going to start with here. So here you can see a rainbow here. So all these colors are colors that makes up the rainbow, from red here and violet here. So these colors constitute what is called visible light. Visible light is light we can see. So all the colors we see are because of light. If you are in a dark room and mean that there's no light there, you can't see any color. But once you switch on a bulb, for example, you'll be able to tell that this is this colored and this is this colored. So the colors are the light we see. So all the colors that we see in our world are part of what is called visible light. So what differentiates the different colors are the wavelength. So this violet here has a wavelength in the range 400 nanometers. So if of course you have the wavelength, it means you also have a frequency here. The thing about electromagnetic waves is they have the same wave velocity. So remember the formula, V is equal to F lambda, where F is the frequency and lambda is the wavelength. So if V is the speed of a wave, and if these have a constant speed, which is 3 times 10 to the power 8, something that it's constant, it does not change. So in the formula, V equals F lambda, you can substitute the value of V, which is 3 times 10 to the power 8. Then if you equate that to frequency times lambda, which is the wavelength, and if you can substitute the wavelength there, you're going to get a frequency. If you use this wavelength, you're going to get a different frequency. So what I'm trying to say is the wavelength here and here are different. So we can say the same about the frequency. The frequency and the frequency here are different. So the color we perceive corresponds to a specific or a range of wavelengths or frequencies on this visible light. Other than visible light, there is also light we cannot see, the invisible light. So the invisible light has different bands or groups of light. So this whole thing is just here. This, as you can see, it's like a rule with, of course, markings here. So these markings are the wavelength. So they range from about 0.0001 nanometer to 100 meters. Okay, so when you go from the visible light here, when you go to the left where there is light we cannot see, there are different bands or groups of light. So there is ultraviolet here. This ultraviolet has a wavelength from somewhere here. So here it's about 400 nanometers to 10 nanometers. So all different types of light that is here is called ultraviolet because of the frequency, and because of this frequency it behaves in a certain way. So if you go to higher frequencies, I mean to lower frequencies, like to 0.01 nanometers, they are what are called X-rays. So X-rays are also different, another type of, or another group of electromagnetic waves with different behavior because of their different wavelength of frequency. After X-rays, they are what are called gamma rays. So on the other side of the visible light, there is what is called infrared, which has a bit of higher wavelength as compared to light. There is also what are called radio waves. So because of they have different frequencies, this different portion of this electromagnetic spectrum, as it is called, this is called the electromagnetic spectrum. So because they have different frequencies or different wavelengths, these different groups or bands of light have different behaviors, so their applications are also different. For example, visible light, we use it to illuminate or to light up our rooms. Well, infrared, it is used in remote control devices. So if you want to, when you are watching watching TV, then you get a remote control, you press on it, so the signal that you are sending travels using infrared. It's light but you cannot see it. Then radio waves, of course, are used in our phones for communication and the likes. X-rays and gamma rays are used in medical applications. So to summarize everything that I've said, so just one more hint or one more point. So the way the electromagnetic spectrum is as you go this direction to infrared and radio waves, the wavelength increases. Well, the frequency reduces, because wavelength and frequency are inversely proportional. The higher the wavelength, the lower the frequency. So that's how it is. That's how the different types of electromagnetic waves are arranged. So now I'm going to highlight the most important points you should get from what I've said. So we're talking about the electromagnetic spectrum. A spectrum is more like a range of things. So a range of these different electromagnetic waves are arranged, of course, according to the wavelength or frequencies, is what we call electromagnetic spectrum. So visible light consists of some colors: red, orange, yellow, green, blue, indigo, and violet. These are the colors that makes up the rainbow. If you want to master them, you can use Roy-G-Biv as a memory aid. So visible light is an example of the electromagnetic waves. Electromagnetic waves are named in the order of the range of wavelength or frequencies. Examples of electromagnetic waves are radio waves, microwaves, infrared rays, visible rays, ultraviolet rays, X-rays, and gamma rays. With that being said, let's take a look at some properties of these electromagnetic waves. So the first is the transfer energy from one place to another. When you switch on a bulb in your room, the light energy from the bulb will move from where it is, from the bulb, of course, to where you are. So that's what this point means. Another property is they are all transverse waves. They are all transverse waves. Remember the types of waves: longitudinal and transverse waves. These are transverse waves, which means the direction of propagation is at right angle or perpendicular to the direction of oscillation. They can all travel through a vacuum. A vacuum is a space without any matter. So these can travel through a vacuum. Remember when we were studying thermophysics, we talked about the movement of it through a vacuum as radiation. So electromagnetic waves can radiate. They can travel through a vacuum. they all travel at 3 times 10 to the power 8 meters per second in a vacuum. So this is their speed. The equation V is equal to F times lambda, called the wave equation, applies to all of them. Despite all these similarities, they have different wavelengths or frequencies, and therefore they have different applications. Now we go to visible light. So we're going to talk about properties of visible light. So first is the light from an object travels in a straight line. Light always travels in a straight line. It cannot make corners, it cannot bend unless something is done to it. Normally it travels in a straight line. So there are two ways to change the direction of light. The first is if you put a surface in front of it. So when you put a surface in front of it, for example, this light which was traveling, if we put something here, then this light can be reflected. So that's one way in which light can change its direction, so through reflection. The second is if the light wave moves from one medium to another. So when that happens, then the light ray we call like a single light wave, we call it a ray. So the light ray is going to change direction if it moves from one medium to another. Such a change of direction is called refraction. We're going to study reflection and diffraction in details. Reflection, we're going to deal with it in this video. Refraction in the next video. So start with reflection of light. So when a light ray from a light source reaches on the surface of an object, the ray bounces off on it. So just like when you have a ball, you throw it down, when it hits the floor, it's going to bounce. So that's the same behavior that light has when it meets a surface. The ray bounces in a regular way on the polished surface such as a mirror. So in a regular way, in a way that you can measure, you can determine. But on rough surfaces, it does not bounce in a regular way. So this bouncing phenomenon of light is called reflection of light. So let's analyze the different parameters that we deal with when we're studying reflection. So when a ray of light is coming, we call that ray as an incident ray. So usually we draw a line which is at 90 degrees to the reflecting surface. This is the reflecting surface, for example a mirror. So we always draw a line which is at 90 degrees to the reflecting surface. So such a line is called a normal. Then the angle between the incident ray and the normal is called angle of incidence. So when a ray of light hits a surface, it is reflected like this. This ray that gets reflected is called the reflected ray. The angle between the normal and the reflected ray is called angle of reflection. So we use the letters I to represent angle of incidence and R to represent angle of reflection. Next, we look at laws of reflection. So the angle of incidence is always equal to the angle of reflection. This is the law of reflection. So I is always equal to R. The incident ray, the reflected ray, and the normal all lie in the same plane. So this we're not going to go into it in details. We can take it as the way it is. These three rays, they always lie in the same plane, not in the opposite plane. You can view a plane as being the one side of a mirror, so, or of a surface. So always it's like that. There is nowhere where the incident ray is on this plane and the reflected ray is on a different or on the other side of the reflecting surface. So we're going to carry out an experiment which is going to aim at verifying the law of reflection, that is incidence is equal to reflected. in terms of angles, of course. So the apparatus we're going to need a light source which can be touch or the sun, a plain paper, a flat mirror, and some cards. So what we're going to have is this is a plain paper. So on the plain paper we're going to put our mirror here, then we're going to get a card. We're going to make a hole here or just a narrow slit so that light can pass. Then we're going to put a light source here. So when we do this, only a small amount of light is going to pass here. So when it passes, it will be hitting the mirror. When it does that, it's going to be reflected. So what we're trying to do is to see if the angle of reflection and the angle of incidence is the same. So to determine the path that the incident ray is taking and the reflected ray is taking, we're going to put pins where we see the light passing from the source to the mirror. So we can put 2 pins, one there and the other one here. Then also we're going to see that some light is being reflected. So again, where the light is passing, we're going to put 2 more pins, another one there, another one there. So when we do that, we're going to connect the pins with straight lines. So we're going to start with this from the incident like this, and the ones from the reflected like this. When we're done, we're going to draw a normal where the line meet, where the 2 lines meet. So a normal should be 90 degrees to where the mirror is. Actually, the mirror can remove it after. First you have to draw a line that's going to represent where the mirror was, and you remove it. So you draw a normal, which is a line at 90 degrees to the mirror. So once that is done, you are going to measure this angle and this angle, and you are going to discover that incidence and reflected are equal. Next, we take a look at a virtual image. So a virtual image is more like a fake image. So usually when you look at yourself in the mirror, what you see is a virtual image. It's not a real image. So the image which cannot be formed on a screen is called the virtual image. You can see your virtual image in a mirror, like I said. So the virtual image in a mirror, so these which I'm highlighting now are what are called properties of a virtual image. So always remember them as the image on the mirror. So the virtual image in a mirror is the same size as the object. So when you look at yourself in the mirror, what you see is of the same size as you. There's nothing like, no, this which I'm seeing has a bigger head than me. No, what you see is exactly as you are in terms of size. The virtual image in a mirror appears at the same distance behind the mirror as the object is in front of the mirror. And finally, the virtual image in a mirror is laterally inverted. Laterally inverted means that right is left and left is right. So for example, if this is a mirror, then if this is the real image, the virtual image will appear like that. So they are of the same size, the distances are the same, and they are laterally inverted. The opposite of the virtual image is called a real image, which is just the image which appears on a screen. So a screen, for example, examples of virtual image is a pinhole camera, which we must have learned in grade 6. I don't know if they're still teaching the pinhole camera. Then also the image we see in movies, it's a virtual image. It's actually an image that has been projected on a screen. That's why we can see it on the screen. Hope I haven't said it's a virtual image, it's a real image, the one we see that can be projected on a screen. So this is an experiment to determine the location of a virtual image. So what you do is you get a mirror like this one, then you put a pin somewhere here, you measure this distance, then what you do is you can view the virtual image from one angle, let's say here. So when you do that, where you're looking at it from, you draw a straight line going into the mirror, then you choose some other convenient angle like here. Again, you see where it is, you draw a line from your eye to where you see the image to be. Once that is done, you remove the mirror and you connect the two lines that you had drawn. Where they are going to meet is the location of the virtual image. So what you are going to deduce from this experiment is this distance and this distance are the same. So this marks the end of part 1 of light. Hope you have enjoyed and happy solving.